To understand why transistor networks are useful, we need to talk about a branch of mathematical logic called Boolean algebra. Rather than go into the full gory mathematical details, I will just illustrate the basic concepts with some not too serious examples. Let's say some friends are choosing a restaurant. Alice is happy when the restaurant serves burgers. Bob is happy when the restaurant does not serve burgers. We can think of evaluating restaurants in this case as something called a gate, an object which takes a binary input, true or false, 1 or 0, and returns a binary output. In this case, the input is whether the restaurant has burgers, and the output is if someone is happy with the restaurant. For Alice, the gate is simple. The output is the same as the input. In electronic terms, the circuit is just a connection. For Bob, the gate is what's unimaginatively called a NOT gate. This is the symbol typically used to denote it. In the previous section, we have seen how this CMOS pair acts as a NOT gate. Let's consider a more interesting example when the logic gates can have multiple inputs. Such gates have pretty straightforward names, as we'll see. Now the friends are choosing restaurants which might serve pizza, noodles, both, or neither. Alice is happy when the restaurant serves at least one of the two options, or both. This idea is represented by what is called an OR gate. This is the symbol. Bob wants choice, so he wants both pizza and noodles on the menu, hence the AND gate. Charlie likes it if the restaurant serves pizza or noodles, but not both. Let's say she thinks that they wouldn't do a good job if they weren't specialized enough. The corresponding gate is called exclusive OR, XOR for short. Each of these gates also has a complementary gate, basically the same gate with a NOT gate after it. For example, the NAND gate gives a 0 when all its inputs are 1, and gives a 1 otherwise. These complementary gates are denoted by the usual symbol with a circle at the output. For a computer, these and all other possible gates must be implemented through CMOS pairs. Connecting two pairs as follows creates a NAND gate. The N-channel and P-channel transistors still work in pairs. Only when a high voltage, or 1, is applied to both pairs of inputs do the paths to high voltage close and the path to ground opens, so a 0 is output. This is exactly the behavior of a NAND gate. The NAND gate is important because it's what's called universal. This means that any other gate can be created out of NAND gates as long as there are enough of them. Now, there are more efficient ways to make certain gates, but in essence this means that the problem of implementing logic gates through CMOS pairs is solved. There are also gates with 3, 4, or as many inputs as necessary. For example, take two AND gates connected as shown here, and they simply become a 3-input AND gate, and so on and so forth. To summarize, logic gates are conceptual mathematical objects which allow us to make deductions based on binary true or false statements. For example, if it's true that today is Saturday or today is Sunday, then it's also true that today is the weekend. We have now seen how the CMOS pairs from the last section can be used to practically implement these gates in terms of electronic binary logic.